All right, get hopping into things here. So we left off last class, and I kind of, told you if we're looking at sample means, we know the mean of those sample means will be whatever the original population mean was from the data you sampled from, and the variance of those sample means, we go back here, will be equal to whatever the variance of the data you sampled from was divided by the sample size. So this is the idea that if we take samples of a higher size, we know we're kind of narrowing down, or we're decreasing this variance of our sample means. So why is that important? So here's a nice little visual. When you think about, this is kind of the underlying data. If I then take a sample of size 5, I look at the sample mean distribution, notice it's going to have, if I'm calculating the standard deviation of that sample mean, because that sample size in the denominator, it's going to reduce the variance of those sample means. So essentially, we said if we have a lower variance, we're getting a more peaked distribution. So if I go from 5 to 50, notice we get a much more peaked distribution. So why is that important, right? And it kind of makes sense, right? Well, I'll hold on for this a second because I think this is a better visual. Let's say I'm looking at a distribution of sample means. Let's do one like that. Let's say I take samples of size 10. Right? If I take samples of size 50, I know that because the variance of my sample means is the original variance of the data I sampled from over the sample size, then when I have a higher number, it's going to reduce the variance that I see from the sample means. So a lower variance means that I have a more peak distribution, so it would look something like this. Now remember, these are both going to be centered around whatever that original population mean is. So when I take a higher sample, what I've done is say, look, the values near that population mean are now more likely for me to see from just taking one sample, right? If I just take one sample, the probability I see this value is like up here, which is now higher than it would have been if I only had taken samples of size 10. So by taking these higher samples, we're really like making sure that the values really close to that population mean are more likely for us to see, which is good because the reason we're taking a sample is in practice because we can't observe what that population mean is. So we want to make sure that if we take this sample, that the probability that it's closer to that population mean is really high, right? If I go like n is equal to like 500, right, I would have something that looked like that, and now I can essentially guaranteed I'm going to see a sample mean that isn't very far away from the population mean. All right? So that's the idea of what we're trying to do. And you can kind of see this here. I choose some different sample sizes. I think the one on the board, it makes it a little bit more obvious, but excuse me. I think about this sample of size 1. Well, the likelihood I see these values right around that mean of 50 isn't very high. But when I take samples of size 50, the likelihood I see these values around that mean of 50 are very high, right? So that's why we want to try to get these higher sample sizes, because it now makes it more likely we see a value from our sample that's really close to the population mean, okay? Or we see a sample mean from our sample that's really close to the population mean, okay? So last class, I didn't really kind of address this. I just said I'm drawing these as a normal distribution. What ends up being true is if I have a variable that I'm sampling from that's normally distributed, the sample means will also be normally distributed. Now we talked about how we find their mean and their variance, but the actual distribution of those sample means, if say I could take samples of size 100 and do that 1,000 times and then draw out their histogram, those sample means will be normally distributed as well. But what if this original variable I sample from isn't normally distributed? Well, we have this thing called the central limit theorem that tells us as long as we take samples of size 30 or more, and so I think here I'll update this and then repost the slides after today. This should be greater than or equal to. As long as I have samples of size 30 or more, we know that the sample mean distribution is approximately normal. Right? It may not be perfect. As we take higher sample size, it's a better and better approximation. But as long as we kind of have a sample size of 30, it doesn't matter what the original data we sampled from started out as. We know the sample means will be normally distributed. Okay? So as we get a larger sample size, we get closer and closer to an approximation. And kind of just a nice little visual. These 4 variables that we start out with here, none of them are normally distributed. We got a uniform, we got, an exponential maybe. We haven't even kind of looked at these, but different types of original starting data distributions, right? If I take samples of size 2, well, none of these sample means are normally distributed. If I take samples of size 6, actually some of these, right here and here, start to get pretty close approximations to a normal distribution. These are still kind of skewed. But once I get to 30, notice no matter what the original variable started out as, all my sample mean distributions now look like they're normal. Okay? So instead of walking through the mathematical proofs, I'm going to walk through a data exercise to help show that no matter what variable we start out with, no matter what distribution it has, the distribution of our sample means, as long as we take samples over 30, will be normally distributed, and their, mean will be equal to the population mean, and their variance will be equal to the population variance over the sample size. Okay? So I started out with this data set where I had all of Indiana births for 2004. So I have the population data. So I can observe what the actual population means and population variances are for Indiana births. I have 4 variables. One is birth weight, gestation or length of the pregnancy, kind of this health measure of the child once it's born, the APGAR score, and then whether or not the mother smoked while pregnant, 1 if she did, 0 if not. Okay? So I look at these averages, right, these means for these 4 different variables from the population data. I can calculate the population means and the population standard deviations. So this is somewhat alarming that, what, 18% of Indiana mothers smoke while pregnant? But, this is what we can kind of look at. So here's just a 1, 0 variable. We've got the means and the standard deviations. So this is the population data. I look at the distributions. Birth weight, one of these biological markers, actually, the original data looks pretty normally distributed, right? Length of the pregnancy, kind of a long left skew, right? We see more premature births, 5 and 6 months. We don't really see 11-month-old babies being born, right? Health score, most babies are pretty healthy, right? This definitely doesn't look like a normal distribution, though. Now, I didn't draw up maternal smoking, but what would that look like? We would essentially have kind of 2 bars there, right? The original variable isn't even continuous, right? The original variable, so 0 if they didn't, 1 if they did, would be like this, right? Where this was 0.82 and this was 0.18. So the original variable starts out not even a continuous variable. But when we take a sample, if I take a sample of 100, I could see 0.23 be the proportion of mothers that smoke, or 0.246, right? I could see continuous values when I look at that sample mean. Okay? So if I'm going to take a sample from this population data, and I take a sample of size 100, I then from that sample of 100 births calculate the average birth weight, or the mean birth weight, mean gestation, mean maternal smoking, all for the mean of each 4 of these variables. I write it down. I then do that 1,000 times. So I take 1,000 different samples of size 100. I would now have 1,000 sample means for birth weight, 1,000 sample means for gestation, etc. Or with 1,000 different samples, I could then create histograms from those to see what does the distribution of these sample means look like. Also, with these 1,000 different sample means, I can calculate the mean of my sample means. I can calculate the variance or the standard deviation of my sample means, right? Like once I have these calculated in an Excel file, this should be very easy, right? Take equals average and equals var.s. Right? So we know from last class that when I calculate these means for my sample means that I've taken, these 1,000 different sample means, it should be very close to whatever the true population mean is, and the standard deviation of my sample means should be very close or equal to, whatever the original population standard deviation was divided by the square root of my sample size. Now my sample size here is 100, so square root of that is 10, right? And that comes from last class. We said there's actually 2 different ways we can write that one equation. So I can write the standard deviation as the square root of the original variance over the sample size, or the original standard deviation divided by the square root of my sample size. Right? That's where that came from, okay? So let's see if that actually holds true. So we looked at the original data. We took these 1,000 different samples. Let's calculate the mean and standard deviation of these 1,000 samples. Okay? So here was the original population mean and population standard deviations that we had. When I looked at those 1,000 sample means, notice, yeah, they're a little off here, but very, very close, right? Some of these are right on, right? This is off by like 1, but really if I looked at the decimal point, this wasn't even off by 1. Same kind of idea here. It's off at the second decimal, right? These are actually, when we round to the second decimal, I get the exact population mean for the mean of my sample means, okay? Now, they're gonna be a little off sometimes if we do this data exercise, because the theory is if I looked at an entire distribution of sample means, which would mean I would need an infinite number of sample means to know what the true distribution, to really replicate those numbers. So this is a data replication that's kind of hits at the idea without me having to walk through and show you guys the mathematical proofs for why this holds, right? But the idea kind of makes sense because you can think about it as, if I was to sample enough times, at some point I would have sampled everyone in the population. So then when I take the mean of the sample means once I've got to the, exhausted the entire population, well, now I'm just taking the mean of the entire population. So that's kind of the idea behind it, right? And this data exercise kind of proves that this holds. Now the standard deviation should be the same as the population standard deviation, but divided by 10 when we look at the standard deviation of sample means. Sure enough, if we divide each one of these by 10, we're getting those exact values. Now these are a little off because I had to truncate it to 2 decimals, but this was like 0.382, it's something really close to 0.038 here, okay? So this, just doing a data exercise like this, you can prove to yourself that these things hold without really needing to completely understand the mathematical proof behind it, right? Because math proofs are, I took a real analysis class in college, and you're trying to prove 1 + 1 = 2, and you have to use like 20 lines, and it's just, it's not fun to look at it. So hopefully, at least now we're somewhat convinced that this holds, right? As long as we get a sample over 30, which we were taking samples of size 100, the mean of the sample means is equal to the population mean, and the standard deviation will just be the original standard deviation divided by the square root of the sample size, okay? Now, I told you no matter what the variable starts out as, if that central limit theorem is met, we also know that the distribution will be normally distributed, okay? So remember, we had birth weight that started out, even before we took samples, looked pretty normally distributed, but what about like maternal smoking? Right? So here's the birth weight, right? If we look at sample means, this is almost a picture perfect normal distribution, right? But one thing that's interesting is, once we look at the sample mean distribution, because we took samples of size 100, we no longer can see a sample mean that is equal to like these really low or these really high birth weights, because it's the idea that if I took samples of size 1, I can see someone who's 7'2". But if I take 100 people, I don't see a sample mean of 7'2", right? There's no way I get 100 random people that their average height is 7'2", right? So once I take 100 different births and calculate the sample means, the values I can see for those sample means, oops, if I can get here, there we go, will be a much narrower range, right? Now I only see values from about 3,000 to 3,500, right? And so this is the idea that, well, I took a high sample, so it took the original variance and divided it by 100. So the variance has dropped a lot, narrowing down kind of the range of values that we're seeing. Right? Same kind of idea for length of the pregnancy. Notice now we get this nice normal distribution, narrower range of possible values. Same thing for the health score. We have a little bit of a left skew still here. We said it's an approximation of the normal distribution. It's pretty close here. And then we have the maternal smoking. The reason why this happens is because when I did a histogram, I probably should have made these bins go from like 0.21 to 0.22 so that you would have more continuous kind of nice looking normal distribution here. But this is a pretty close approximation, okay? It's going to give us a pretty close approximation. So even with a variable that starts out not even continuous, once we look at the sample means of that variable, those sample means will have this nice kind of continuous distribution where we can see any values from those samples, right? Any questions on this? This is more so just you kind of believe what I'm saying, right? Without having to understand mathematical proofs, this is what's happening, right? And then I said assign a bunch of different continuous probabilities. Then I tell you that the central limit theorem makes them irrelevant, right? So I mean, it doesn't matter what we start out with. Once we have samples over 30, we know those sample means will be normally distributed, right? So we don't even care about the original data, how it's distributed. Also, if you guys, does anyone know what this movie is? Yeah, you should all watch The Big Lebowski. It's a great movie. I don't know. I hope some of you have seen it. Anyways, I digress. So once we know that this is true about the sample means, it looks really similar to what we were doing when we had population data. So first question I have to ask, do I have a sample size 30 or higher? Once I do, I know that I'm going to have a sample mean distribution that's a normal distribution. I'm going to know its mean. I'm going to know its variance. Well, I can convert any normally distributed variable into z-scores or a standard normal distribution. I then can, so that equation is going to look like this, and I'll come back to this in just a second. Once I have that z-score, I think about what region am I looking for. Maybe I want to find the probability that the sample mean I see is, I don't know, below 39. Well, I can convert that 39 into a z-score, look that z-score up on the table, and find the area to the left, which would be that probability, right? Now, we might have another step, which, well, what if I want to know the probability it's greater than 39? Well, then I'd have this fifth step of subtracting it from 1. So once I calculate that z-score, these steps, it's the same thing we were doing before. It's nothing new, right? It actually looks no different. Now, this step is a little different, right? The z-score equation looks a little different, but why? It's actually the same thing we were doing before. So, my marker's running out of juice here. How do I want to think about this? So we've got, this was our z-score equation when we were looking at the original population data, right? Well, if I know that my sample means are normally distributed, and the mean of my sample means is just the population mean, and the variance of my sample means is just the original variance divided by my sample size. When I find a z-score, I look at whatever variable I'm looking at, I subtract its mean, and I divide by its standard deviation. Well, now the variable I'm looking at is the sample mean. So when I'm creating that z-score calculation for the sample mean, well, now instead of looking at cutoff values of x, I'm looking at cutoff values for this variable that is the sample mean. I'll then subtract the mean of my sample means and divide by the standard deviation of my sample means. Well, what are these two things? Well, the mean of my sample means is just the population mean, so I'll plug that in. The standard deviation of my sample means is the square root of the variance, so square root of the original population variance divided by my sample size. Right? So that's why the equation is a little bit different. Now I could rewrite this a little bit, where the denominator is like that, right? We talked last class. There's two ways to kind of write this, right? They both mean the same thing, it's just a little bit different. And just so I don't confuse you, right? The numerator, I'm just saying these two equations would give me the same thing, right? Now, what I want you to remember is that this represents the standard deviation of sample mean. So it's really no different than what we did before. It's just now we don't need the mean and the standard deviation of this variable x. We need the mean and the standard deviation of our sample mean, because that's now the variable we're looking at, okay? But once we have that z-score, everything looks the same, all right? So I'll walk through a couple examples here with you. So let's go first here, all right? So let's say I've got this normally distributed variable. I know its population mean, I know its population variance. I then want to take samples of size 100, right? What's the probability that's between 10 and 15? Okay. Now, there's kind of something weird going on with these slides, so it looks different on my computer. So I just want to make sure you can see this. This is sample mean, right? It kind of just looked like X, there we go. It kind of just looked like X before because it was running into the line above. But we're looking at what's the probability that the sample mean we see from this sample of size 100 is in between 10 and 15, okay? So what I'll do is think about what area I'm looking for first. Well, I'm looking at sample means, and I know they should be normally distributed, and the mean of my sample means should be whatever that population mean was. I think the original variable, the population mean was 5. Now the variance of my sample means, I'm going to write this in the spot where it's glaring, so let me write this down here. for the video. Okay. The variance of my sample means, we said it was just the original population variance over my sample size, so 2,500, wait, my samples were size 100, there we go. Okay? So I have the mean and I have the variance of this distribution. Now we go to that z-score equation, right? We said that denominator was actually representing my standard deviation for my sample means. So I could just take the square root of this guy, which ends up being 5. Okay? The question then asked, what's the probability we're in between 10 and 15? All right? So I didn't leave myself a ton of room here, but as long as we have these, I'm going to rewrite this up here just so we remember what it is. Okay? Everybody okay if I erase this? Okay. So first of all, what do I know this area has to be less than? Or what's this probability have to be less than? There's usually a similar answer. Well, less than 100 for sure. I mean, what does it for sure have to be less than? The probability has to be less than 1. But here I can actually go a step further. I can say it also has to be less than, what's the area to the right of the mean? 0.5. This is an area that's smaller than the area to the right of the mean. So right away I know it has to be less than 0.5. Okay? But I can find the actual probability by turning this into a z-score. Right? I'll turn 10 into a z-score, 15 into a z-score. I want the area in between the two. We actually already worked through a problem like this. Once we get the z-scores, I find the probability I'm below this one, the probability I'm below this z-score, subtract the smaller from the larger one, and I'll be left with the area that's in between. Now, how do I find these actual z-scores? Right? Well, what we could do is say, I'll take that cutoff value I'm interested in, 10, subtract the mean of my sample means, which is 5, divide by the standard deviation of my sample means, which is also 5, and I get a z-score of 1. Okay? Now, I could have done this different. If I wouldn't have calculated that standard deviation first, another format we had of this equation was the square root of the original variance over the sample size. Well, remember, this denominator just represented that standard deviation of my sample means, but to find the standard deviation of my sample means, we need to use this equation, right? Well, I could actually just plug the values in here, right? The original variance was what? So the square root of 2,500 divided by 100, and I would get that same z-score of 1. Either way is fine. I personally, instead of dealing with that other formula, we're going to go through some more statistics where you always subtract the mean of whatever statistic you're looking at and you divide by the standard deviation of that statistic. So for me, it makes more sense. Calculate what that standard deviation is, and then you just have to plug that value into the denominator. I just have to plug that 5 in there. But if you want to like substitute in what the equation for the standard deviation is into that formula, you can do that, right? You're just kind of skipping an intermediate step and you're just building it all into one formula. Okay? Does that make sense? Any questions on that? We're okay with that? You sure? Okay. So I'll also point on this one. I could find what the z-score for 15 should be. This is another thing that helps. How far away is 15 from 5? 10? I'm not trying to trick you here. What's the standard deviation of this normal distribution? 5? How many standard deviations away from 5 is 15? 2, right? So it should have a z-score of 2, because that's the definition of the z-score. It's the number of standard deviations away from the mean that we are. Okay? If I go ahead and plug in instead of 10, 15, you want to verify that, you enter in your calculator, you'll get that z-score of 2. But with these nice, easy numbers, knowing that definition of the z-score, it's easy to recall that. Okay? So we got to finish this out. We actually, oh, I did not mean to do that. There we go. So once we transform these into z-scores, right, you can think about what we have. Oh, there we go. Stop. Okay, I won't use my mouse because apparently I'm. All right, there we go. But I can find the area to the left of a z-score of 2, subtract the area to the left of that z-score of 1. This would cancel each other out, and I'd be left with what I was originally looking for, right? How did I find these values? It's the same way we did before. Look at that z-score of 1 and that z-score of 2. Go to the tables. Z-score of 1.0. Oh, I lost this in class. Give me 1 second. Stop this. See if I can get this back on here. Why isn't it like that? Let's try this. Hold on, I'm having technical difficulties here. I don't know why it switched off of that. No. Switch back to the computer. There we go. All right. So I go to this standard normal table. I look at that z-score of 1.00. The area to the left is 0.8413. Go down to that z-score of 2.00. The area to the left of that was 0.9772. Right? Once I have those values, I'm just subtracting that smaller area from the larger area to get left with what's in between, which is what I originally wanted. 0.9772 minus 0.8413, we get 0.13. Now, there's an earlier slide that we did this week that looks exactly like this, because once we get to the point where we've calculated z-scores, everything's the same as what we were doing before. The only real difference was when we were calculating these z-scores, finding 1 and 2, right? We had slightly different equations. So I put them up here like you didn't calculate the intermediate step. Remember, if we had just found this ahead of time, this was just 5, and we could plug in that 5 there. Right? So really the same thing, it's just now we have a slightly different equation for what that standard deviation is. It's the standard deviation of our sample means, not just the original variable that we sampled from. Okay? Let's work through another example here. So let's say we have that length of pregnancy variable. We got a mean of 39. We got a variance of 9. Right? We take a sample of size 81 from that original data. Of those 81 infants, what's the probability that the sample mean I see will be greater than 39.5? Okay. So what's the probability to be greater than 39.5? And so I can remember these numbers in my head, but I'll be using them here when I go to the board. Right? So it's just the exact same thing we did before, but we've got some different values to work with. So I know that I've got my sample means. I took a sample of size 81, so I know it's normally distributed. That central limit theorem is met. The mean of my sample means is whatever the original population mean was from the data I sampled from, which I think was 39, we were told, right? I know the variance of my sample means will be equal to, actually here, let's do the standard deviation of my sample means. And for the video, I'm going to write over here so it's not in the glare. Kind of in the glare. So that's just going to be the square root of my population variance over my sample size. Well, here I was told the population variance is 9, and my sample size was 81. So this ends up actually being 1/3. Okay? Now, the question was, what's the probability I see 39.5 or anything greater? Right? So what I can do, it's a normally distributed variable. I can convert this into a z-score. I want the area to the right. When I look this up in the table is going to give me the area to the left. Right? But once I have the area to the left, how would I find the area to the right? Just, yep, 1 minus that, right? So if I think about this, if I look at these possible answers, I just want to kind of hammer home a couple other points here before we work through the entire thing. What do I know this probability has to be less than right away? If I look at this area has to be less than 0.5 because the area to the right of the mean is 35. If I have a number that's to the right of the mean, the area to the right of that has to be then less than 0.5, right? It's a smaller area than the area to the right of the mean. Now, if I look at those answers, there's only 2 that meet that criteria. 0.0668 and 0.4332. Now, initially, you might think, if I'm just trying to guess, right, you might look at that and say, well, man, the value I'm interested in is really close to the mean. So if I thought it was really close to the mean, I might say, well, then the probability will probably be fairly close to 0.5, right, the area to the right. The problem with that thinking is before, when we're looking at just the original data, standard deviations are kind of big. So if you see a value really close to the mean, like 0.5 away from the mean, usually it would have a probability close to 0.5. But once we look at the distribution of sample means, the variance of those sample means is impacted by the sample size you take. So if the original variance of the data was 9, but I take a sample of 81, well, we said, right? My standard deviation is only 1/3. So even though 39.5 is only 0.5 away from the mean, that's more than 1 standard deviation, right? It's actually like 1.5 standard deviations away. So I need to be careful when I think about, like, I'm trying to bound it, like just how I'm thinking about the problem even before I go to the formulas, because it's not just about the distance away I am from the mean, it's how many standard deviations am I away from the mean. And when we start dealing with sample means, these standard deviations can get low pretty quick, right? If I take a sample of size 200 here, that standard deviation is going to be really small, right? Then seeing 39.5 is going to be really unlikely, okay? But I can actually go ahead and solve this, right? So I have this equation for finding the z-score for my sample means. So I plug in my cutoff value I'm interested in for the sample mean. I subtract the mean of my sample mean. I then divide by the square root of the population variance over my sample size. Once I have that z-score of 1.5, it's just like what we were doing before, right? I look that area up in the table. Sorry, there we go. That area to the left of a z-score of 1.5, or the probability I saw something 1.5 standard deviations above the mean or any lower or anything less, would be 0.993. But what we wanted, remember originally, was the area to the right. So I then needed to subtract that from 1, and I get that probability of 0.0668 for that area to the right of that z-score. Okay? Now for this equation here, what I could have done was, instead of saying, okay, I know the z-score is going to be this equation will always work, and that's fine. That's how I had it presented in the slides. But remember, this is just representing the standard deviation of my sample means. If I already had that calculated, instead of entering, you know, the 9 and the 81 here, I could have just plugged in 1/3. Right? Either way, whichever way makes more sense to you. Like I said, I personally like to draw it out, calculate the standard deviation, and that's just easy for me to think about. I'm throwing that number in the denominator. If it's easier for you to have that formula in front of you that looks like this, that you always plug those values in, then that's okay too, right? I think, how do I say it? If I don't have a better understanding of what's going on, this might be a little bit easier because I'm just plugging the numbers in. If I have a better understanding of what's going on, I think this method is going to be a lot easier to deal with. As we work through more examples, hopefully this will make, hopefully we'll kind of conceptually be able to understand this more and more as we work through this. Are there any questions on that before I keep going? I'm going to introduce something a little bit different, and then we'll kind of pick up on Monday with it. Okay with this? Let me check in the chat. Okay. So, something very similar we can do holds for the sample proportion as well. So when we talk about proportions, This is actually like thinking about that maternal smoking variable, right? Because when I was looking at the mean for that, if I took a sample of 100 births and I looked at did the mother smoke or not, I have zeros and ones. When I'm finding the mean there, I'm actually just finding the proportion of mothers who smoked, right? So if I have a sample proportion, kind of from this binomial distribution, right, we can think about we have ones and zeros, the other smoked or they didn't. We can from that know that, well, look, if I'm trying to turn this mean, which represented the number of successes I see, into a probability, all I would do is divide by the total number of observations. So n over n, I'd be left with the mean of those sample proportions should be whatever the original population proportion was. Just like the mean of my sample means was whatever the original mean was, population mean. Now, a little bit trickier if I think about here, the variance of the variance on the population proportion. Well, here, remember, this was the variance when we're looking at the number of successes. If I want to convert that into the proportion of successes, I would just divide by n. So I'd have p times 1 minus p. And then for my sample proportions, I would take that variance and divide it by n, right? Just like we did, we took the original population variance for the sample mean and divided by n when we were looking at the sample mean. So if I'm looking at sample proportions, the equation for the variance of my sample proportions is take the variance on the population proportion, which would just be p times 1 minus p, and divide it by my sample size. So I want the standard deviation. As always, just take the square root. Right? So you don't have to completely understand that this is all kind of linked together. You can kind of take this as gospel, but it really does come from the binomial where we have the number of successes. If I want to turn the number of successes into proportions or probabilities, I just divide by the total number of observations I have, which is n. The n's cancel. So I know the mean of my sample proportions is equal to p. The variance is equal to the variance on the original population proportion divided by n because I'm looking at my sample proportions now, okay? But if this is true, we can do everything that we did for the sample means for the sample proportions, right? So as long as the central limit theorem applies, we could do an example like this. What's the probability I get 54 or more heads in 100 coin flips? So I'm actually going to just draw this out and then we'll kind of go back to the slides because I think me working through an entire example will help. So we wanted the probability of seeing 55 or more heads out of 100 coin flips. Okay? So instead of sample means, we're now thinking about the distribution of sample proportions. As long as the central limit theorem applies, we saw with that maternal smoking variable, they'll be norm and distributed, and the mean will just be whatever the original population proportion was. With the maternal smoking variable, it was 0.18, right? We saw that the mean of my sample means, I was telling you it was a mean there, but really all a proportion is the mean of a 0, 1 variable, right? Because if you think about what I'm doing there, if I were to add up that maternal smoking variable and divide by the number of numbers I have, that's the mean calculation, right? But this maternal smoking variable, when I look at the actual data, it's either a 0 or a 1. So let's say it goes 0 plus 0 plus 1 plus 0 plus 1. All this is doing, when I find the mean of a 1, 0 variable, it's going to find the number of people who did smoke and divide it by the total number of observations. So when I find the mean of a 1, 0 variable, it's really just giving me the proportion of people who smoked here, right? So it is a mean, but it works a little bit differently, right? Because it's a 0, 1 variable. So for a coin flip, we know that the sample proportions should be centered around what value? If it's a fair coin, the population proportion should be 0.5, right? Okay, so the variance for my sample proportions was p times 1 minus p divided by my sample size. And actually, keep doing this. I'm right in that glare spot for the video. I don't like to do that. So p times 1 minus p over the sample size, right? Well, all I do there is plug in 0.5, 0.5, and I believe I said 55 out of 100. So my n here would be 100, 0.5, 0.5, okay? I then wanted the probability I saw 55 or more, which would be a sample proportion of what? 55 out of 100, that's just a proportion of 0.55, right? So right away, I know this area I'm looking for, the probability has to be less than 0.5 because the area to the right of the mean is 0.5. But what I can do is I can turn, this is a normal distribution, I can turn these into z-scores, right? How do I turn 0.55, sorry, it's 0.55, into a z-score? Well, every z-score equation is what statistic are you looking at? Now instead of the sample mean, I'm looking at the sample proportion. Subtract the mean of the statistic you're looking at and divide by the standard deviation of the statistic you're looking at. Okay? It's the same format. So now what's the mean of my sample proportions? Well, that's just the population proportion. What's the standard deviation of my sample proportions? Well, it would be the variant, the square root of the variance. So the square root of p times 1 minus p, or the population proportion times 1 minus the population proportion, divided by the sample size. Hopefully you can see that. So it's all the same thing. It's just now when I look at that z-score equation, it's a little bit different, right? But if I ahead of time calculate that standard deviation, and I know that the mean of my sample proportions is just the population proportion, I can just plug in values here, right? So it's the same procedure as what we did with the sample mean, but a little bit different, right? The equation might look a little bit different if we don't kind of do the intermediate steps. So we'll work through kind of here. Got the values here. So I can plug in my population proportion. I'll keep that denominator so that we get a kind of, we don't do the intermediate step here. I get a z-score of 1, right? If we look up a z-score of 1, we looked it up earlier. The probability is going to be the same as it was earlier. We get 0.8413. We wanted the area to the right, so we'll subtract it from 1. Right? Once we get to the z-score, everything's the same as what we were doing before. And none of the procedures are different. Right? Are we on time here? We got one more example, I think. Let me make sure I have one more example. Yeah, we'll go through one more here. Whoops. So this one's a little bit different. So what's the probability of getting 66 or more coin flips in 144? Sorry, what's the probability of getting 66 or more heads in 144 coin flips, right? Well, if it's a fair coin, then we know the population proportion is going to be what? Still 0.5, okay? So what I'm thinking about is I've got my sample proportions. I know they're normally distributed. I know my population proportion should be 0.5. My sample size was 144 coin flips. What is the cutoff value I'm interested in? Well, I said it was it 66 out of 144? So it's just 66 over 144, which, I don't know if I have my calculator. Does anybody want to help me out if you got a calculator in front of them there? So 0.458. So just so we have a placeholder value here. So I know that my sample proportions will be centered around that true population proportion. I know I want the probability that it's greater than approximately 0.458. So right away, I know the probability that I'm looking up has to be greater than what value? Yeah, right? The area to the right of the mean is 0.5, so we're looking for an area greater than that. Now I'll show you how we would do this a different way. I think it makes a little more sense. So let's say, we're going to go down here. We want to turn this into a z-score. But I'm first going to calculate the standard deviation of my sample proportions. Okay? I know that that's equal to the square root of my population proportion times 1 minus my population proportion over my sample size. Okay? So once I have that value, right, I know that I can just plug that into my denominator for my z-score equation. Right? And technically, this would have been what's the mean of my sample proportions? Well, I know that's just whatever the population proportion was. So that's why I could kind of think about this as, 0.458 minus 0.5, and then divided by whatever this ends up being. Right? Or I can do it all in one step, and I can like plug this whole thing in the equation and just enter it all in my calculator at once, whichever way is easier for you to think about. Okay? So I'll turn that into a z-score. Once I have this z-score, I can find the area to the left. Remember, I wanted the area to the right, so just like before, we would then subtract it from 1. Okay? So if we go here, we have all of our values to kind of double check this. So right away, we said it had to be greater than a probability of 0.5, so we know it's going to be either B or D. We plug everything in. Lo and behold, we get a z-score of -1, right? Where are we at in time too? Oh, wait, we're good. So I look up that z-score of -1. So -1.00, 0.1587, right? So the area to the left, oh my gosh. I got to get a less sensitive mouse. There we go. It's 0.1587. I then subtract that from 1, and I get my answer of 0.8413, okay? So like I said, once you get that z-score, like nothing's different. I mean, once we get that z-score, everything's the exact same. We use the standard normal table the same. Nothing changes there. It's really just how do we think about these z-scores? So I think what happens to some people is we see these equations I give you for the z-score and they look different, right? And I put them up there because that if you want to do it all on your calculator at once, the equation you actually do want to use, right, would look like, oh, where do I have it kind of? Well, I think I had it up on the board here, so. Would look like this. So you could see I had it written down earlier. Right, that is actually what it is. But if you remember that this just represents the standard deviation of whatever statistic you're looking at, you can always calculate this first and then just plug that value in. Just like when we were looking at the z-score for sample means, we could have written it down like this. Or we could remember that that denominator just represents the standard deviation of our sample means. Calculate that ahead of time and then just throw that in the denominator. Okay? And we'll be looking at other statistics too. And we always do the same thing. We subtract the mean of that statistic and divide by the standard deviation of that statistic. We'll just see that as we progress, these standard deviation equations start to become a little bit more complicated. Okay? But the sample proportion and sample mean are really the same thing. And what that really hinges on is you're just taking the mean of a 0, 1 variable. So let's see, I'm not sure if I have something in this data set that would work. But I do have. I think we had something in here maybe that worked for us. Yeah, right? If I wanted to find the proportion of females, if I take the average of this 0, 1 variable, well, why is it? Oh, this is all females. So let's do married. Maybe that'll be a little more interesting. Right? It'll just tell me the proportion of people in this data set that were married, right? Approximately 50% here, right? So it's really, the proportion is a mean. It's just the mean of a 0, 1 variable, okay? So you guys have got that Connect assignment. I've had a couple of you email me up questions on that, so it's good. I know you're working on that. Try to get that knocked out as soon as possible, and then you have the individual assignment, which is more about things that we talked about, like the log normal, exponential distribution, and actually dealing with your own data. So I already had somebody contact me about slightly changing what data they were using. That's fine. I got something sent back to them right away. Get working on that, and if you feel like your data set doesn't work for the problem, although I think most of yours should, let me know your concerns, and I can try to kind of tell you how to specific to your data set, how you can progress with the assignment, okay? All right, have a good weekend, and I will see you guys on Monday. Well, not you guys, but the other group.